So we were discussing about this particular problem, right? Okay. So now can you quickly just note down the problem and data? Meanwhile, I will see the other students, those who are joining or not. So just take down the questions and let me know the answer. That is the first part, stagnation pressure at the compressor inlet they are asking. Stagnation pressure. So we have discussed about the all the formulas in the last class. So quickly we will just go through in this one. So they have given the temperature T1, they have given P1, they have given, and the velocity is also given. When the velocity is given, that means T01 will not be equal to T1, right? When the velocity will be 0, then we can say that stagnation will be equal to static, right? Yes or no, guys? Right. But here they have not given anything about those conditions. So what we are going to discuss? So we are going to apply the steady flow energy equation. We are going to use the steady flow energy equation first of all. So from or we can not make use of the steady flow energy equation directly. We can just write, H01 will be equal to what? H1 plus V square divided by 2. So Cp into T01, Cp into T1 plus V square by 2. V1 square, because velocity V1 is given to you. So from here, what is the T01? T1 plus V square divided by 2Cp. 2Cp. Now by different here, and of course, we need to multiply with the 2000 so that the unit can be maintained at what? Kilojoule per kg, right? I think you are very well aware of those things, right? So T01 will be 255.7 plus 250 square divided by 2, 2000 into Cp. What is the Cp value? 14 kilojoule per Kelvin. And they have given what? Standard air, right? They have given ambient air. Ambient air means we can consider atmospheric air, and that is what? Ideal gas. So for ideal gas, we know that Cp value is what? Constant, that is Cp will be equal to 1.005 kilojoule per kg Kelvin. Understanding? From here, what is the T01 value? Tell me the answer. T01. Yes. What is the value of T01? 286.8 Kelvin. 286.8 Kelvin. Approximately we can write like this. Once we get the T01 value, my dear friend, how to get the values of stagnation pressure at that point, at that location? What is the stagnation pressure, right? What will be the stagnation pressure? So we know that the formula. What is the formula we know? P01 divided by P1. That we can write T01 divided by T1 to the power what? Gamma divided by gamma minus 1. Where gamma is equal to gamma for ambient air will be what? 1.4. Gamma value will be, adiabatic index will be 1.4. That is known to us. So P01 will be P1 54.05. T01 is what? 286.8. T1, what is the T1 value? 255.7. So this value will be 1.4 divided by 0.4. So from here, what is the P01 value? Suppose you will calculate, you will be getting what? 80.77 kilopascal. That is the answer for first question. That is the answer for A part. Understanding my point? Tell me guys. Perfect. Now suppose you need to calculate the compressor work. You can use the steady flow energy equation, of course. H1 plus V1 square divided by 2 plus del Q. H2 plus V2 square divided by 2. Of course, we can write 2000 plus del W. My dear friend, this value is what? H01. This value is what? H02. This is 0. So can we say delta W will be the whatever the compressor work is there, the required compressor work will be, see here compression work will be what? Negative, right? So work of compression will be what? Minus of W. Understanding my point? Because we are giving the work input to the system, that is what? Negative. So delta W will be what? Minus of work of compressor. So work of compression will be what? Work of compression will be what? Okay, first complete this part. Or let me just note on the equation. So H01 that is equal to H02 minus work of compression. So work of compression will be H02 minus H01. That is equal to Cp into T0 minus T01. So without knowing any velocity further at the stream at the location 2, we can calculate the work of compression just by knowing the values of T02. T01 we know, T02 we need to calculate, right? So before that, just complete this slide. Understanding what is happening? Do not confuse. At the inlet condition of the diffuser, the pressure is atmosphere pressure. The temperature is atmosphere temperature. They clearly mention ambient air is first decelerated in a diffuser before it is entering. That means whatever these things are given, that is given at this section. From here to here, section 1 to section 2. Why we are calling this to be H01? You know that H0 is what? H plus V square by 2. So if 1, 1, 1. If it is 2, 2, 2. So first complete this part, then we'll move on to the what? Compression work. That is the second part. And they are asking per unit mass. So we need not to calculate anything about mass flow rate. So my dear friend, here Cp is known to us, T01 is also known to us. T01 is nothing but 286.8. Cp value is 1.005 kilojoule per Kelvin. Now we need to calculate the values of work of compression. Before that, we need to calculate the values of T02. Again, we are going to use the same formula. T02 is equal to what? T02 by T01. That is equal to P02 divided by P01 to the power gamma minus 1 by gamma. But what is the P01? P02. What is the P02? P02 by P01, they have mentioned clearly stagnation pressure ratio. That means you know that the in compression pressure will be rises. In compressor pressure will be rises. So P02 by P01 will be 8. So from here, what is the answer for T02? 519.5 Kelvin. That will be the answer for stagnation temperature at that location. Now, if you just put the value of work of compression, you will be calculating as 233.9 kilojoule per kg. That will be the answer for part B. Understanding my point? Okay. So just note down. No, they will not be asking. Just we are doing. See, actually, this is a basically we are taking the session for HL examination only. But whatever the portion that will be may be required for HL examination already covered, or some portion we will cover in the today's lesson. That is shock wave, oblique shock, normal shock, and expansion wave. Those things we will cover, right? Convergent, divergent, nozzle. Some of the interview question also we will try to understand today, right? So theoretical question will be coming. Do not worry, but these things will make you understand the subject and the topic that is actually going on, right? Without solving the numerical, you will not feel, sir, what is actually happening. Same thing you are doing in the, thermodynamics also. There you are calculating Cp T1 minus T2 because there you know the velocity actually. So directly you are calculating in terms of Cp T1 minus T2. In fact, if you are using normal compression, with those compressor that is not used in the, the basically normal, that is not used. Suppose those compressors which are used in the aircraft and the normal compressor that is not used in the aircraft will be different. In that case, velocity will be almost negligible at the inlet and outlet section of the compressor, right? Only varying thing will be pressure and temperature only. Velocity will not be that much affected in the compressor. But here they have given the velocity. That's why we are calculating in terms of that thing, right? Understanding my point? Correct. So now on the next topic, isentropic flow through nozzles. So here many interesting phenomena will be coming when the flow will happen through the nozzle. Then what are the changes will be happening? What are all the changes happening in the properties of the fluid? That is also we are going to cover. So very first assumption that we are considering over here is isentropic flow. Very basic assumption we are covering over here is isentropic. That means there is a no friction and there is a no heat transfer to the surrounding. No friction, no heat transfer to the surrounding, to or from the surrounding. No friction, no heat transfer to or from the surrounding. That means it is an insulated one. Now try to understand isentropic flow through the nozzle. First of all, whenever we talk about the nozzle, very basic picture that will be coming to your mind is, convergent nozzle, convergent duct. Am I right? Whenever we just assume and think of this convergent nozzle, the naming itself is suggesting that it must be some kind of convergent thing. Understanding my point? Tell me guys. But here you should be worrying, we are talking about the subsonic nozzle. When it is a subsonic nozzle, things will become very good thing for us. Whatever we are assuming, that is whenever anything will be converges, that converging part and the converging duct will be called as nozzle, because function of the nozzle is what? To increase the velocity. And of course, you can verify this thing from the area ratio formula. What is the area ratio formula? dA by A is equal to m square minus 1 into dB by V. So as we keep on moving like this, so area will be what? Decreasing. This thing will be negative. Here subsonic flow, that means what? Mach number will be less than 1. That is also going to be negative. Negative, negative will become positive. So dV will be what? More than 0. That means the velocity is what? Increasing, my dear friend. The velocity is what? Increasing. This is positive. That means what? Velocity is what? Increasing. Whatever the inlet velocity is there, exit velocity will be more than the inlet velocity. And whenever the function will be, whenever the velocity will increase, our function will be fulfilled. And that purpose is what? For that purpose only we are using nozzle. But the condition is subsonic flow has to be there at the inlet of the nozzle. Understanding my point? At the inlet section of the nozzle, the flow must be subsonic, right? Yes or no, guys? Perfect. Now, whatever the things I will tell you, try to understand. Try to understand. Few things are very important over here. Okay, can I remove these things? Okay, fine. Now try to understand. Let me consider, or I can take you to the next slide. Try to understand. This is a nozzle which is being connected to the reservoir. Reservoir means through which the flow is happening. Through which the flow is happening actually to this one. This is what we have, the reservoir. This is what we have, the reservoir, my dear friend. This is what the nozzle we have. Adiabatic nozzle. Here, whatever the pressure is there, P naught, temperature is T naught. Because velocity is 0, so we are calling what? Everything to be stagnation property. Whenever velocity will be 0, then at that point, whatever the velocity will be there, whatever the properties will be there, that property will be called as stagnation properties. Right? Now this has been connected to some chamber. This chamber is being connected to the pipe wall. This is what chamber. This is the wall. Pressure adjusting wall. Pressure adjusting wall, my dear friend. Now try to assume the flow direction is something like this. Now try to understand. The moment, my dear friend, I'm drawing the pressure distribution along the length of the nozzle. Try to understand this thing. This is a very fundamental thing. Because if you are not able to understand this converging nozzle, you will not be able to understand converging diverging nozzle, right? So that's the main thing. Now, here, first of all, what will happen? Suppose my pressure is what? P naught. At the exit, suppose my valve is closed. If my valve will be closed, any flow will happen through this valve? Or maybe whatever the accumulation of the fluid will be there, that will be still in the reservoir. It will not be flowing in the nozzle as well as, what you say, in the chamber or through the wall, because valve is closed. That means I'm maintaining the pressure called P1. Suppose I'm maintaining the pressure to be called P1. Suppose. Now, my dear friend, what will happen when I open the valve? What will happen when I open the valve? Here I am calling PB, back pressure. The pressure which we are maintaining at the back of the nozzle, we are calling back pressure. What is this? Back pressure. As we just slightly open the valve, what will happen? The flow will happen through this one and the pressure in the chamber will start reducing. Suppose pressure is over here, P2. The pressure is P2 over here. So whenever what is happening, I'm drawing two graph. I'm drawing two graph. X is something like this, and this is what the pressure. Here I'm drawing mass flow rate through this particular nozzle, as well as I'm drawing PV divided by P naught. That means how much of back pressure I'm maintaining at the exit of the particularly chamber or at the exit of the nozzle. So when I maintain the pressure P1, when I maintain the any pressure P1, tell me any flow will happen. Mass flow rate will be 0, right? The mass flow rate will be 0, right? When I maintain the pressure P1, the mass flow rate will be 0, right? Tell me guys, mass flow rate will be 0, right? When I maintain the pressure P1, the mass flow rate will be 0. The moment I decrease the pressure like this, the moment I decrease my pressure from P0 to P2, from P0 to P2, the moment I decrease the pressure from P0 to P2, the mass flow rate will increase. The mass flow rate will start increasing, right? Again, if I further open the valve to the pressure P3, then what will happen? Again, further what will happen? Here P3 is less than what? P2. P2 is less than what? P1. What will happen? Again, mass flow rate will increase. Again, mass flow rate will increase. Suppose if I maintain P4, again mass flow rate will increase. But there is a one pressure will be coming. That pressure will be called as P star. P star, where even though after reaching to the values of P star, let me call this to be P star only, not P4. Let me call this to be P star only. The moment the pressure will be back pressure will be reaches to P star, the mass flow rate will be maximum. Even though you reduce further, P5 will be less than P star, but there will not be any changes in the mass flow rate. That is the maximum mass flow rate you will be getting at the P star value. Further, you do P5 or P6, the value will not be changes. So these are the values corresponding to 1. These are the values corresponding to 2 point. So please note on the graph, that is a very, very important graph. The moment the mass flow rate is going to be maximum, that condition we call choking condition. You know the choking conditions? What you are asking? I thought like the upper and the lower part of the water will be there itself, so that the center of the line water only moves. No. See, there is a reservoir, there is some kind of fluid will be there. That particular fluid may be air or whatever the gases will be there that is flowing through the nozzle. That will how the flow will happen. What will be the mass flow rate through this particular nozzle to the chamber to the wall? That depends on the how much of pressure we are maintaining, how much of wall we are actually opening. Understanding my point? So here what will happen? The moment the maximum mass flow rate will be reached at this point, what we are calling maximum mass flow rate, achieved at P star value. This condition is called choking condition. This condition is called as choking condition. Please note down. Whenever the mass flow rate through the nozzle is reaches to the maximum value, that is called choking condition. That is a very, very important, my dear friend. But tell me at what Mach number this choking is happening. See, initially Mach number is less than 1. What will happen to the Mach number? What will happen to the Mach number? Tell me, guys. Yes, this maximum mass flow rate is happening at Mach number 1. When Mach number reaches to the 1, when Mach number reaches to the value 1, there itself we are getting what? Maximum mass flow rate, right? When the velocity of the fluid will become sonic speed, the velocity of the fluid will become what? Speed of the sound. In that case, my dear friend, whatever the mass flow rate will happen through the nozzle, that will be at the peak value, that will be maximum value you will ever get from the nozzle, right? Understanding my point? Correct. So this is a very, very important and fundamental thing. Very, very important. Please note down. So what will be the condition for maximum discharge? Condition for maximum discharge. Mach number should be equal to 1. Mach number should be equal to 1. That is a condition for mass flow rate, maximum mass flow rate, right? That is the main thing. So here what you will observe, the same thing has been depicted over here. This is the adiabatic nozzle where there is no heat transfer is happening through the to the surrounding, and how the pressure distribution is there. So whenever there is no pressure variation, no mass flow rate. As we keep on decreasing the pressure, mass flow rate will keep on increasing in the nozzle. But the moment it is reaching to the what? Mach number 1, further you reduce the pressure, what will happen? The mass flow rate will not increase. Of course, one more thing you want to try to understand this thing. Why the mass flow rate will happen through the nozzle? What is the driving force for flow through happen in the pipe? You consider just like a nozzle to be what? Just like a pipe only. What will be the driving force in the pipe? Pressure difference, right? Pressure difference, right? Yes. So whenever there is a pressure difference will be there, then only the mass flow rate will happen through that section. So the greater the mass, greater the pressure difference, greater the mass flow rate. But there is a one condition where further you try to increase the driving force, the mass flow rate will not increase. That condition is called choking condition. That's the reason, my dear friend, maximum to maximum Mach number, maximum to maximum velocity you can achieve at this second point, at this second section will be Mach number equal to 1 or Mach number will be less than 1. Maximum to maximum you can get Mach number 1 only in the converging nozzle. You will never get supersonic speed. But the question is why? Question number 1. Okay, let me write. Okay, done this one. Note it down. So the first question will be, why supersonic flow cannot be achieved by converging nozzle? In fact, converging subsonic nozzle. That means at the inlet subsonic flow is there, and there is a converging duct. So that is called subsonic nozzle also. Sometimes we call subsonic nozzle, sometimes we call converging nozzle. That is the first question. Question number 2. Question number 2. Okay, we will try to answer first of all the question number 1 only. Then we will try to discuss the question number 2. Tell me guys, why the supersonic flow? See here what is happening. Mach number is less than 1. By the flow area ratio, when area will be decreasing, Mach number is also what? Decreasing. The velocity is what? dB by v is what? Positive. That means the velocity is increasing, but why the velocity is just equal to what? C only. Maximum to maximum. Why the Mach number 1 only we are getting? Why not Mach number 1 is not possible over here? In fact, velocity is increasing, but why it is not increasing beyond one value? Have you ever come across this thing? Just think and tell. Just think and tell. Why supersonic flow cannot be achieved by the converging or subsonic nozzle? Tell me guys. Yes, any answer, any answer. It need not to be correct. Whatever the answer is coming to your minds, just try to give me. See, you only observing that from the area ratio, the velocity is positive. That means velocity is increasing. By why we are not able to increase more than Mach number 1? Suppose you might be thinking, sir, we can attach, more converging part. That means whatever the part is there, extra we can converge further. so that the velocity can be increased by decreasing the area. Is it possible so? Before this was the section. Now further you want to attach, suppose, more converging part in order to think that, in order of thinking that you might be, predicting that the Mach number can be more than 1 here. Not here. Suppose Mach number equal to 1, but here I will be achieving the Mach number more than 1, but not possible. In fact, by doing so, you are reducing the mass flow rate by decreasing the area of the flow. Because what is the mass flow rate? Rho into A into velocity. Velocity you are not able to achieve because whatever the Mach number 1 is there, further, suppose it is less than 1, here also you will be getting Mach number less than 1 only, or just equal to 1. So there is a slight increment in the velocity, but there is a drastic decrease in area. Further, it will reduce the mass flow rate. By attaching more converging part, you are only reducing the mass flow rate. You are not increasing the speed. Then what is the scope? What we can do? That is the first question. Second question, why we are not able to achieve? That is the main question. From the subsonic flow, right, air which is coming into the missile or a jet aircraft, they are subsonic speed. Whatever the normal speed that is there. But at the exit, suppose your rocket is there. Your rocket is there. Now you want your rocket to be, fly at a very, very high speed, at a very, very high altitude. For that, my dear friend, suppose 5,000 kilometers if you want to achieve through this particular rocket, you want to travel the distance of 5,000 kilometers through this particular rocket. For that, thrust need to be produced, right? Tell me, guys. Thrust need to be produced like anything. What is the thrust value? What is the thrust value? Mass flow rate into velocity. Mass flow rate you cannot increase. You already know because of the choking condition. Because of the choking condition, mass flow rate cannot be increased. Velocity you can increase like anything, my dear friend. That means at the exit, suppose you are attaching, see, of course, I am talking about the convergent, divergent nozzle. But suppose, my dear friend, velocity has been increased drastically. Suppose by some chance we are able to increase the velocity, the thrust force will be very, very high. By Newton's third law, the ground will offer more thrust force, more force. It will offer more force to the rocket, and it will send the rocket to the what? Very, very high distance, very, very high height. Understanding my point? That's what the rocket is actually happening. Whatever the phenomena is happening in the rocket. Understanding my point? But why the shape of this, whatever the combustion chamber is there in the rocket, why it is not of the shape of like this? Why it is shaping like this? Converging, then diverging. That means, suppose this is the converging portion. To have the supersonic speed from here to here, we are attaching one diverging section also. Why it is so? Why we are not able to achieve through a further converging part attaching? That means further if you are attaching, can't we produce the high thrust? No, that is not possible. So to sustain the mass, no. Mass flow rate will decrease, but not drastically. Understand my point? That is not the matter of concern. Matter of concern is thrust force that has to be produced in a larger quantity, in a larger magnitude, so that your rocket can fly up to the maximum height. Right? That is the main concern. So for that, my dear friend, let me explain you reason for this. Why we are not able to achieve the maximum supersonic speed through the converging nozzle. Understand? This is your reservoir. Your reservoir, your nozzle. Suppose this is a chamber, my dear friend. Whatever the velocity of the flow direction is there, that is a positive x direction. But what will happen to the disturbance? What will happen of the disturbance? Disturbance means pulsation wave. The pressure wave. Pressure wave will be flowing in the what? Whatever the pressure wave will be there because of this throat and valve. Whatever the valve is there, whatever the throat is there, whatever the pipe is there, whatever the chamber is there. Suppose moment the flow is happening, the disturbance will be flowing in the opposite direction. Understanding my point, what I'm saying? In the starting of the lecture, I mentioned one point. Whenever you take the piston cylinder arrangement, there's a piston. The moment you try to compress the fluid, what will happen? The disturbance will start propagating, but that is in the opposite direction. And that disturbance will be propagating. See, what is the meaning of disturbance? That will try to disturb the flow direction. And that is disturbance that is propagating at a very, very high speed, that is called speed of sound. That is the speed of the pressure wave, right? Now, and of course, because of that only, my dear friend, suppose the moment you reduce the pressure over here, try to understand. This is a very, very important reason. You will not find anywhere. The moment you try to open the valve, the pressure will decrease. The pressure will be decreasing. That means what? The pressure will be decreasing. That message will be propagating to the reservoir. See, it is just like a communication will be happening between two person, the person over here and person over here. This person is saying, I have reduced the pressure, my dear friend. Please try to communicate my message to this person. From person number 2 to person number 1. The person number 1 is sitting to the person number 1 is sitting in the reservoir. He will say to the reservoir, please, the pressure has been reduced. You try to increase the mass flow rate. The reservoir will say, okay, boss, we have just increased the mass flow rate. Further, we have reduced the pressure. This person will be felt that, okay, the pressure has been reduced slightly further. Then again, it will communicate to the person number 1. And again, that person will be communicated to what? Reservoir. And the reservoir will say, okay, we are just increasing the mass flow rate. Just hold on. After that, what will happen? The movement, what will happen? The velocity of disturbance with respect to fluid, we can write velocity of disturbance minus velocity of fluid. Yes or no, guys? From the vector mechanics, can we write velocity of disturbance? Vd is what? Velocity of disturbance. Understanding what I'm saying? Vf is velocity of fluid. Try to understand. The velocity of disturbance with respect to fluid is flowing with a sonic speed that is in the opposite direction with the vector called c. With the vector called c. That is the speed of sound. C is what? Speed of sound. Pressure wave will always flow through with the velocity called speed of sound only. Remember. Now, what about the velocity of disturbance? That we need to calculate. My dear friend. What is the velocity of the fluid? The movement at this section, Mach number will be equal to 1. The velocity of fluid will be what? Speed of sound. This will cancel out. This will be cancel out. Velocity of disturbance will be 0. What will happen, my dear friend? Further, my dear friend, the moment you reach the Mach number, even though you reduce the pressure further and further and further, even though you reduce the pressure lesser than P star or choking pressure value, if you reduce further also, that person will be just handless or helpless. He will not be able to communicate, because for communicating, how he is communicating between 2 and 1, is just going through like this, like this, like this, and reaching to that person with the velocity called velocity of disturbance. When the velocity of disturbance will be 0 meter per second, it will not be able to reach, and it cannot tell to the ear of the person number 1. When it cannot able to reach to the person number 1, the person number 1 cannot tell the story to the what? Reservoir, that pressure has been reduced. And if there is no communication between 1 and reservoir, you know that the mass flow rate will be still the same. Further, there is no increase in the mass flow rate. Now you understand when the Mach number will be 1, why the mass flow rate is maximum. Check it out. So that's a very, very important thing. Please note down. It's a very, very important question, guys. Once it is done, let me know. Just note down. Done, all of you? Perfect. So that is what the condition, my different. With the help of converging nozzle, only the purpose of the nozzle will be what? To just we can use this particular subsonic nozzle used in the Pelton wheel, right? In the Pentel wheel, what is happening? This is a suppose what we have the blades. So whatever the nozzle is there, which is coming from this penny stock to something like this. Now this will be what? This thing will be just converged to the nozzle so that the velocity can be increased. Understanding my point? So that's the only purpose that subsonic nozzle will be used in the hydraulic machines. Understanding my point? Yes or no, guys? So you can just note down the converging nozzle we can use in hydraulic turbo machines. Understanding my point or not? All of you understanding? Yes. Check it out. Perfect. Done. So now you got to know that definitely we need some further additional modification in the geometry. That means we need to divert the portion. That means we need to divert the portion so that we can get the supersonic speed. So shall we discuss about the convergent divergent nozzle? Very, very important, guys. Done. Perfect. Now, not only convergent divergent nozzle, we also call CD nozzle. So that's a very, very important thing. So when we think of the nozzle, we generally think of the flow passage. When we think of the nozzle, we think of the flow passage, how the flow passage is happening, whose cross-sectional area decreases in the flow directions. When you think of the nozzle, you will think that, okay, the cross-sectional area might be reducing in the flow direction. However, the highest velocity of the fluid can be accelerated in the converging nozzle is limited to the sonic velocity, that is Mach number 1, which occur at the exit plane, that is throat plane. And accelerating the fluid to the supersonic speed is not possible by attaching the converging part. We have to attach the diverging part. Now the reason is, sir, how that phenomena can happen, how we can increase the velocity. Now let me explain you that. Try to think and just think of it. Suppose I said that this is the nozzle, right? Mach number less than 1. Yes or no, guys? Yes or no? So this is the flow direction. This is a subsonic flow at the inlet of the nozzle. Subsonic flow at the inlet of the nozzle, first of all. Now from the area ratio formula, we know that Mach number, when area will be decreasing, Mach number square minus 1 will be what? Mach number less than 1 means what? It is also negative. So dV by V will be positive. That means velocity is increasing. That means what? It is a nozzle. It is just behaving like a subsonic nozzle. Suppose the velocity has been increased, but still the Mach number is what? Less than 1. That means Mach number is what? 0.6 Here the Mach number is 0.8. Suppose by further attaching my different, what is happening? Again apply the area ratio. Again apply the area ratio. Again apply the area ratio. Area has been increased. Area has been increased. Again, this is also negative. Still it is negative. Then what about the velocity? What about the velocity? Will decrease. Check it out. Please check it out. Please check it out. So can I call this to be nozzle? No, my dear friend, we can call this to be diffuser. Understanding my point? And now any one of you can please tell me where we have seen such a type of convergent, divergent, this subsonic CD, part, where we have seen this thing, where we have seen the subsonic. That means flow throughout the section from inlet to outlet will be subsonic only. That means if you draw the Mach number, this is the Mach number 1. So what is happening? What is happening? Now tell me where the Mach number will be. Mach number will be here. It is max. Here it is 0.6. Where the Mach number will be more? Definitely here it is not possible. Here or here, at the throat or at the exit. This portion is called as throat portion. Tell me guys, this is a very, very important discussion. Yes. Where the Mach number will be maximum. Check it out. Mach number will be maximum where the velocity will be maximum. Mach number will be maximum where the velocity will be maximum. Where the velocity will be maximum, again we can just get it by the area ratio formula. So it is just like a, what we say, Brahmastra. That is a very, very killing instrument we have. So this is what the formula, m square minus 1, everything depends on this particular formula only in this particular compressible flow. So now Mach square minus 1, what is this value? What is this value, my dear friend? This is not equal to 0, right? Mach number is not equal to 1. That means this value cannot be 0, right? This term cannot be 0, right? This term cannot be 0, right? Check it out. Perfect. That is a perfect thing. Now, for maximum velocity from the mathematics, from math, you know that dv by dx, or suppose you are taking along the x direction, dv by dx must be equal to 0, or we can say dv must be equal to 0. If dv must be equal to 0, dA by A must be equal to 0. Again from the mathematics, if dA by A will be 0, so again we can just write like this. So what about dA by dx? dA by dx will also be equal to 0. If dA by dx will be 0, that means it is just talking about, from the mathematics point of view, it is just talking about the minimum area and the maximum area. And of course, physically we can understand that they are talking about the minimum area. Through this location, we are going to get the minimum area. Now everyone, even blind person, can tell you where the area is minimum. Inlet section, exit section, or at the throat section. Where the area is minimum. At the throat only, my dear friend. At the throat only. At the throat, what is happening? See, if I just zoom it, it is like this. If you just consider two sections in the throat, area changes will be 0. It is just like a flat line. So whenever the area will be 0, there the maximum velocity is there, my dear friend. And of course, from here, what will happen? The Mach number will increase, reaches to the 0.8, and again further it will decrease. So that is what the Mach graph. Please note down. Understanding my point? And everybody know this example. This is not the converging diverging nozzle that we use in the aircraft, rocket or jet aircraft. This has been used in famous example in the fluid mechanics. We already cover Venturi meter. Yes or no, guys? There we have the nozzle, throat, and the diverging portion. Check it out. To the pipe, to measure the discharge value, we just attach what? Venturi meter, right? Please check it out. Perfect. Absolutely perfect. Please note down. This is a very, very fundamental thing. In the book, they have not mentioned anything about, my dear friend, even though you follow any standard textbooks. So this thing will come when you try to understand, you stick with the fundamental thing. Your mathematics is good, everything will be fine. So still, if somebody is thinking that if we are attaching the, to this particular converging part, if you just attach to the diverging part, I will be super cool and I will be just getting the maximum flow rate to be through this one. And of course, we will be getting what? Velocity to be more than C. In thought of thinking Mach number more than 1, that means you are fool. At the exit, my dear friend, at the exit, how much of Mach number you are getting, that depends on at the throat, how much of Mach number you are achieving. If the Mach number will be less than 1, throughout the section, Mach number will be less. That means Mach number will be less than 1. That means throughout the section, the flow will be what? Subsonic flow. Or one more condition is there. Even though you reach Mach number 1, at the exit, you can get supersonic flow and subsonic flow. Understanding the point? If you are attaching, if you are just reaching to the values of Mach number equal to 1, at the exit, you will be getting supersonic flow and the subsonic flow. That depends on the back pressure. Understanding my point? That depends on the design pressure. How much of design pressure you are maintaining? How much of valve you have opened? Understanding my point? Are you understanding what I'm saying? So just by thinking the convergent divergent part, if somebody is thinking that if I'm having CD nozzle, I can fly the rocket like anything, that means you are fool. So everything depends on the design condition, how much of design pressure you are maintaining, and how much of Mach number has been achieved at the throat section. Right? So that is a very, very important thing that need to be considered while understanding this convergent divergent nozzle. Of course, this has not been used in the rocket because velocity is decreasing, my dear friend. Thrust force will not be able to produce. The opposite reaction forces cannot be produced by the earth to the rocket. The rocket cannot fly to the particular height. At a very, very high height, you cannot fly the rocket. And of course, if you're not able to do that, you cannot do the whatever the satellite is there, you're just attaching the satellite to the particular portion. You cannot do that because satellite position is not just above the 1 kilometer or 10 kilometer or 20 kilometer or 2000 kilometer. It is way beyond that. Understanding my point? For reaching that value, we must throw the rocket at a very, very high speed, at a very, very high thrust forces. Now, done? Perfect. So just note down these things, very, very important. Forcing a fluid through the convergent divergent nozzle is no guarantee that the fluid will be accelerated to the supersonic velocity. In fact, the fluid may find itself decelerating in a diverging portion instead of accelerating if back pressure is not in the right range. Right? So that's a very, very important thing. The state of the nozzle flow is determined by the overall pressure ratio PB by P naught. Therefore, for a given inlet condition, the flow through converging diverging nozzle is governed by the back pressure. That will be explained. I told you, right? See, you are getting this Mach number lesser than throat Mach number. Who will decide? Who will decide? There's no rocket science is going on, right? There's no prediction is going on like just by reading any book. It is just happening how much of back pressure or design pressure you are maintaining at the wall. Understanding my point? Depends on that. If the wall is fully open, then what will happen? The flow will happen like anything. Further, you are reducing the pressure, the flow will happen like anything, such that the velocity will increase and the Mach number graph will be like this. At the throat, it will be 1, and at the exit, it will be more than throat. Suppose you are maintaining the design pressure. Actually, whatever the design pressure is there, if you are maintaining that one, then you can get the what? Supersonic speed. Understanding my point? Understanding my point, what I'm talking about? Right. So try to think in a theoretical manner also. Try to talk with yourself so that you can understand this topic, because this topic is very, very difficult just by what is the difference between fluid mechanics, what you have studied, and now whatever the fluid mechanics you're learning, just the density changes. Just by changes of this thing, everything got changed. Everything got changed. Whatever you are learning right now, subsonic speed. Subsonic means density effect is negligible. That's what you are studying in the 1 meter. That's why you are able to apply the Bernoulli equation, because one of the assumptions in the Bernoulli equation is incompressible flow. Subsonic, there will not be that much variation in the density. So we can assume to be what? Negligible density variation. Understanding my point? Nowhere at this section you are getting maximum velocity. That means what is happening? What is happening, my dear friend? Mach number is very, very low. Yes or no? Velocity is low means Mach number is low throughout the section. If Mach number is low, compressibility effect will be low. Now, and of course, you can see through this particular diagram. You can see through this particular diagram what will happen. What is happening over here? You are taking one converging divergent nozzle, Mach number less than 1, and here, of course, at the throat, Mach number equal to 1. The moment you are reaching to the Mach number 1, if I draw the Mach number profile, Mach number equal to 1. The moment you are reaching Mach number equal to 1, Mach number equal to 1. Let me draw exactly to that location. The moment you are reaching Mach number equal to 1, at the exit, you will be getting Mach number more than 1 only, my dear friend. Right? Because even a fool person can tell me that if Mach number is increasing from 0.6 to 1, further there is no way of decreasing that, because what is happening? Suppose we have maintained the design pressure in such a way that what will happen? We have maintained the design pressure in such a way that this is a design pressure. We are maintaining the design pressure in such a way that it is a very, very low pressure, such that the velocity is what? Increasing, my dear friend. If velocity will increase, the moment here, it might be possible that Mach number will be more than 1. The moment Mach number will be more than 1, apply the area ratio formula. Just more than 1, 1.01. Suppose this will be positive, this is positive, dV by V will also be positive. Understanding my point? Velocity will increase like anything, and we will be getting the flow to be what? Supersonic flow. Understanding my point? Check it out. Suppose you are not able to reach Mach number 1, then the discussion might be happening. Okay, where, see, again, dA by A, m square minus 1, dV by V. Now, suppose some of you are having the confusion, sir. Suppose you are telling here the maximum Mach number is there, but before the discussion of you, suppose I want to know where the maximum velocity I will be getting when the Mach number is equal to 1 here over here. Suppose Mach number is equal to 1 over here, then what will happen? This is going to be 0. Because of that, this is going to be 0, but this is not equal to 0. Understanding my point? So at this location, definitely the velocity will not be maximum. Understanding or not? Where the Mach number is equal to 1, where the area research, whatever the changes in the area will be 0, where the minimum area is there, where the Mach number equal to 1, that is called a throat portion, there the velocity is not maximum. Velocity here also not maximum. There is only one possibility. Velocity will be maximum at this section. Understanding my point? All of you, check it out. And again, if you are thinking like that, then again you might be confused. Mach number can be decreased also after reaching to one value. Again, that depends on pressure value. Suppose pressure value is much higher than the design pressure, then God cannot save you. If you are maintaining the design pressure such that the velocity will increase, my dear friend, then the maximum velocity you will be getting at this location. But if you're not maintaining the back pressure to be more than, suppose lesser than this value, more than that value, the flow will not be maximum, mass flow rate will not be maximum, velocity will be minimum. Understanding my point? What if, I will discuss. That is what the next point, when the design pressure will be varying. That is our next discussion, my dear. Now, once it is done, let me know. Once it is done, let me know. Done? Perfect. Try to understand the pressure variation in the convergent divergent nozzle. That's why the naming has been given convergent divergent nozzle. We are not calling convergent nozzle and divergent diffuser. Ever we just ever you just heard the name convergent nozzle and divergent diffuser in the rocket? No, right? You always say nozzle, because when you just attach Mach number less than 1, here also velocity is increasing, here also velocity is increasing, and only one instrument is there who is having the function to be increasing the velocity. That instrument is called nozzle. So this is also called nozzle. This is also called nozzle. That's why the naming has been given. That's the naming has been given. Hello, I'm audible. Yeah. So just note on the diagram. Just wait. Just wait. I'm coming. Yes. Hello. I'm audible. Perfect. So convergent divergent nozzle is there. So now you got to know that in the venturimeter, whatever we are using, that convergent divergent, that is different. That is a subsonic. But here, the subsonic flow to supersonic. The moment we are getting supersonic flow, everything got changed. Everything will be changes. Now, how the things will be changes, that is a very, very different phenomena. So first of all, let me discuss convergent divergent. This is a very, very fundamental discussion will happen over here. This is my throat portion. And of course, I can draw the inlet section like this. So we'll try to see the pressure value. So first of all, we are going to discuss how much of back pressure we are maintaining. Suppose when the pressure is what? Just equal to whatever the pressure is there. Suppose P naught. Suppose P naught pressure is there. Suppose P naught pressure is there. Suppose the pressure is same as P naught only. Let me call this to be A point. Any flow will happen? No, right? No flow will happen, right? Suppose you maintain the back pressure, design pressure as P naught. No flow will happen, right? Now, further, my dear friend, what will happen? Further, what will happen? You decreases the pressure value. You decreases the pressure value such a way that you decreases the pressure value to the point B, but this now whatever the back pressure is there that you are maintaining equal to PB. B point, whatever the pressure is there, I'm calling PB. Understanding my point? Whatever the back pressure is there, now you are maintaining PB, which is lesser than P naught. Now tell me flow will happen. Now tell me flow will happen. Now tell me flow will happen. Flow will happen. You have reduced the pressure. Somewhat you have reduced the pressure than inlet pressure. There is a driving force has been created. The flow will happen. The flow will happen. Suppose Mach number is less than 1. Suppose the Mach number less than 1. Now, I'm not drawing this, let me call this to be basically the Mach number. Suppose Mach number equal to 1. Suppose, yeah, at this point, what is happening? Mach number is less than 1. Now, suppose we have reduced the back pressure to PB, but not in a very high quantity. We have slightly reduced the pressure such that the still Mach number is what? Less than 1. If it is less than 1, here also you will be getting less than 1. Yes or no, guys? There is a no doubt if Mach number will be less than 1, then here also Mach number less than 1 only. Check it out. Yes. So what will happen? This will behave like a nozzle. This will behave like a nozzle and this will behave like a diffuser, as I discussed. For subsonic flow, this will behave like a nozzle and this will behave like a diffuser. And in that nozzle, you have understood in the fluid mechanics from the Bernoulli's theorem, P by rho g plus V square by 2g equal to constant. When velocity will increase, pressure will decrease. That is what happening. But the moment velocity will decrease, the pressure will increase, like recovery pressure. Check it out. Check it out. Whether this thing is clear? Perfect. Perfect. Now, the next part, you further reduce the pressure to point C. You further reduce the pressure to point C. Like this and like this. That means still we have the subsonic flow. But my dear friend, suppose you have reached to the maximum condition. I'm taking the maximum condition to be, suppose, C dash. C dash is corresponding to choking condition. Now you have reduced the back pressure to P star. I'm calling this to be PC dash. Hello, I'm audible. Just wait for 2 minutes. Actually, just now power gone actually in my area. Just wait. Hello. Yes. Yes, I'm audible. Now, let me just call this to be, let me call this to be C dash, C star. I'm calling this to be C star, something like this. That means choking pressure condition. That means whatever the choking condition is there. Just wait. So I'm calling this to be my choking condition, my dear friend. That means I'm getting what? Choking condition. But when the Mach number is equal to 1, this pressure is corresponding to when the Mach number has been reached to the what? Exactly equal to 1. Now at this point, there is a two possibility. Either the flow can be subsonic. When the flow can be subsonic, when the flow is subsonic through the diffuser, then the pressure will increase. Yes or no, guys? When the flow through this diffuser is subsonic, then velocity will decrease, pressure will increase. Understanding or not? Check it out. Perfect, perfect. But I told you there is a two possibility when the Mach number is equal to 1. Suppose the design pressure, is what? So this is corresponding to choking condition. C star, this value is what? C star. But now suppose there is a two possibility. One is what? Subsonic flow, and other is what? Other is what? Supersonic flow. And this is corresponding to E point. Now, my dear friend, you might be thinking, sir, why in the supersonic flow through this particular divergent portion, when Mach number is more than 1, try to analyze what will happen. Velocity will increase, pressure will decrease. Yes or no, guys? When the supersonic flow is happening through a diverging portion, then the pressure will further decrease. And after reaching to the Mach number 1, this is what corresponding to Mach number equal to 1. This point is corresponding to Mach number equal to 1. That means at the throughout Mach number is equal to 1. At that point, my dear friend, there's a two possibility. One is this one, and other is this one. The point can be reached to the point C star, and the point can reach to the E point. Please note down till this part. Now the game will start. Just note down. Just wait. I need to check. Power is actually came, so I need to check my connection, Wi-Fi connection, whether it is happening or not. Just hold on for 1 minute. Hello, hello. I'm audible. Hello. Can you please confirm? Yeah, correct, correct. Now, my dear friend, you got to know that there is a one question. There is a one question. You know about the sock? We will come back. First of all, note down this diagram. Then we'll come back to this diagram. This diagram is over, all of you. This diagram is over, all of you. Check it out. Now, I will come back. But before that, I would like to discuss about sock. I would like to discuss about the shock wave. I would like to tell you about the disturbance wave. I would like to tell you about the pressure pulsation wave. What is happening? What will happen when the normal shock, when the oblique shock will produce? For understand those things, suppose, my dear friend, suppose you are maintaining your back pressure. You are maintaining your back pressure in between. in between point C dash and point E. Suppose you are not maintaining, suppose you maintain the back pressure exactly at the point C dash, C star, you will be getting subsonic flow. But suppose you are maintaining the design pressure is at the PE, you will be getting supersonic flow. There is a no doubt about it. Understanding my point? It is corresponding to supersonic flow without any shock. Yes or no, guys? No disturbance, no shock, nothing is going to be producing. Simply we'll be getting what? Supersonic flow. Our purpose will be fulfilled. But suppose you are not able to maintain the pressure exactly C star or E. Suppose you are maintaining the pressure to be PD. Suppose you are maintaining the pressure to be PD at the back pressure. I'm talking about the back pressure. Definitely one possibility is there. Definitely one possibility is there. Mach number will be exactly equal to 1. See, after location to the 1, when the Mach number is reaching to the 1, suppose Mach number is equal to 1. After that, what will happen? Velocity will increase. Mach number will increase. Now suppose that it is keep on happening along the supersonic zone. It is at this point. Suppose my fluid element is exactly at this location where it is just flowing like anything and is just there at this location. That means along the supersonic flow, the flow is happening through the particular diverging portion to be what? Supersonic. Suddenly, my dear friend, he is getting the back pressure to be just not equal to E, more than D. Now tell me how it can match PD value from here to here. Tell me, guys, how it is possible to match this pressure to be what? Suppose at this point the pressure to be D dash. Suppose now it has to match with the PD value. How it can match? Through a suddenly jump. Through a suddenly jump, or there is a discontinuity will happen. There is a suddenly increase of the pressure will happen from PD dash to PD, because it has to meet the condition, right? The design pressure is what? The back pressure is what? PD only. Understanding what I'm telling? Your back, see, design pressure is PE. Design pressure is PE. There's no doubt. Sorry, whatever the PD is there, I'm calling design pressure. Design pressure. Do not confuse. PD dash. This is a design pressure. Now, whatever the pressure I'm maintaining is PD, but it is flowing through a subsonic flow. Suddenly, you got to know that exit pressure is what? PD. Exit the pressure is not 20 kilopascal. Exit the pressure is what? 10 kilopascal. Suppose 50 kilopascal. It has to reach to that particular pressure value. How it can able to reach? Suddenly there is a jump will happen. Suddenly the pressure will increase, and this is corresponding to normal shock in divergent portion. And there is a discovery of normal shock. No doubt. Very, very important. Very, very important. Suppose you have maintained the pressure to be, suppose PG. Suppose you have maintained the pressure to be PG. Suddenly the pressure is coming like this, fluid is coming like this, and suddenly it is getting some information that some communication, he is getting the communication from the backside, and that the pressure has been increased from PE to PG. Then it will be reaching to this way by the jump. This is a symbol. This is a symbol of normal shock. Understanding my point? Normal shock means the disturbance that has been happening in the flow, the disturbance which is happening in a perpendicular to the flow direction, that disturbance we call normal shock wave. Understanding my point? Shock wave means there is a multiple type of shock wave here. We have normal shock wave, oblique shock wave, we have, and we have the expansion shock wave. But the wave or the pulsation or the disturbance that has been, this is a disturbance. This has been created in the flow direction, whatever the flow direction is there, and that disturbance direction is there perpendicular. That's why the naming has been given normal shock. Understanding my point? whatever the plane of shock will be there, that is a perpendicular to the flow direction. That's why the naming has been given normal shock. Suddenly there is a jump in the fluid pressure. The fluid is reaching from this pressure to this pressure. How? No rocket science. Nothing is there because of normal shock. If suppose you would have maintained the pressure to be PE, simply he will be flowing like this, like this. There is no jump at all, no shock at all. But you try extra smart and you just plate that the back pressure to be what? PD or PG. Then there will be normal shock. Suppose you are very much greedy and you still want to have the maximum mass flow rate through the nozzle, through the particular converging divergent nozzle, and you maintain the pressure to be PI. Then what will happen? Nobody can stop you by destroying the rocket like anything. You will be having expansion shock wave outside the nozzle. Expansion shock wave, outside the nozzle. Or simply not, I'm not calling expansion wave to be shock wave because it is beneficial for us. Expansion wave outside the nozzle, not inside the nozzle, outside the nozzle. Very, very important. Still you have reduced the pressure like anything. PI is what? Less than PE. That means you are very much greedy. You are further reducing the pressure so that you are thinking the driving force has been increased and the mass flow rate will also increase further. That is not going to be happening. An expansion wave will be created outside the nozzle. Within the nozzle, we are perfectly fine. Nothing is there. No shock is there. But after that, here, the shock will be producing, and that is my different expansion shock wave. Very, very important. Very, very important. Suddenly, my friend, that is a so specialty about the shock wave. So remember, when you talk about the normal shock, subsonic flow, supersonic flow. See here, what is there? Supersonic flow, right? PD dash is supersonic flow. Am I right? PD dash is a supersonic flow, right? From the supersonic flow, suddenly it has to be converted to what? Subsonic flow. Subsonic flow. Please note down, very, very important. Now, once it is done, let me know. Once it is done, let me know. We'll discuss about the, normal shock. So note down, shock wave that occur in a plane normal to the direction of flow. This is the flow direction and the shock wave is something like this. This is the plane of shock. When both are perpendicular, then we say it's a normal shock wave. The flow that process through the shock wave is highly irreversible. Highly irreversible. Of course, adiabatic, highly irreversible. Then whatever the approximation is there, that is isentropic, that cannot be fulfilled. I told you, for isentropic, the flow has to be reversible and adiabatic. Understanding my point? Yes or no, guys? Yes or no, guys? Perfect. So irreversible, normal shock means irreversible plus adiabatic. Adiabatic, why? Because nozzle is still insulated. No heat transfer can be taking place. Whatever the friction is there, because of the friction, whatever the heat energy will be generated, that cannot go outside. Still it is adiabatic. It is what? Insulated, my dear friend. Still it is insulated. Everything is what? Perfectly insulated. Now, so what is so specialty about this basically, normal shock? Remember, normal shock always occur in the diverging portion. Always occur in the diverging portion. That is also one of the very, very famous interview question. Why the suppose the convergent divergent nozzle is there, but why the shock is not produced in the nozzle? Why it is produced in this particular converging diverging part, not in the converging part? So here, whatever the wave front is there, suppose here it is Mach number more than 1. After the normal shock, Mach number will be less than 1. That means pressure will increase, has to be increased. There is no doubt about it. Are you understanding my point or not? The pressure has to be increased. Why it has to be increased? Irreversible entropy generation. Entropy generation means what? Delta S of the system. And from the thermodynamics, you know that, sorry. What is happening? Just wait. So suppose here, Mach number more than 1, because of the normal shock, Mach number will be less than. That means supersonic flow will be converted to subsonic flow always. Supersonic flow will be converted to subsonic flow always. Supersonic flow will be converted to subsonic flow, my dear friend. But pressure will increase. Why? You know that it is a highly irreversible phenomena plus adiabatic phenomena. Together combination, we are calling this to be normal shock. That is a specialty about the normal shock. Irreversible means entropy generation cannot be zero. How to calculate entropy generation for the open system? Or you can take for the closed system, delta S of the system, right? Plus delta S of the surrounding. So for surrounding, it is zero because there's no heat transfer has been happening. So what are the delta S of the system? Cp ln T2 by T1 minus R ln P2 by P1. Understanding or not? Yes or no, guys? Perfect. So note down. These are the very, very important thing. Please note it down. Very, very, very important. So if entropy generation is not equal to zero, then what will happen? Pressure will increase. Temperature will also increase. Why the temperature will also increase? Why the temperature will also increase? See, subsonic flow means what? Velocity will decrease and that will lead to pressure will increase. Understanding my point or not? Velocity will decrease. Whatever the kinetic energy will be there, that has been converted to what? Friction energy, heat energy, or thermal energy. That's why the temperature has been increased, right? That's the reason temperature has been increased. Understanding or not? And then we have velocity will decrease, density will also increase, entropy will also increase. But what about the stagnation temperature? Will be fixed, right? H01 will be still equal to what? H02, because for this one we have never said that it has to be irreversible. Only condition is what? Adiabatic condition, and still we have adiabatic condition. Tell me, guys, are you able to follow all the things what we have discussed in the first class? Without that, it is impossible, believe me, impossible to understand even a single topic from this compressible fluid flow. But P02 will decrease, or simply you can say stagnation pressure will decrease. Stagnation pressure will decrease because of irreversibility. Because of irreversibility, stagnation pressure will decrease. All the static property will increase. All the static property will increase. Note down, guys, very important. Done all of you? Is it done? Done all of you? Yes. So now actually when you just see from this correlation, see this is because of irreversibility, the stagnation pressure has been reduced drastically. Now due to that, what is happening, you can understand from here also, P02 is what? P2 T02 divided by what? T2 to the power gamma minus gamma by gamma minus 1. Here at this section and this section, the flow is isentropic here to here, here to here. But from here to here, in between this, suppose you want to apply I to E, the flow is can never be assumed to be what? Isentropic. But before normal shock and after shock, what we can assume? We can assume is still the flow to be what? Isentropic. Understanding my point? That's why I am able to apply what? This correlation. Yes or no, guys? All of your understanding? So here what is happening? The T has been increased drastically. T2 has been increased drastically. In fact, T2 effect is more than the P2 effect. P2 is also increasing. So you might be thinking P02 will be increasing, right? But that is not true. T2 is increasing in such a very high quantity that it is reducing the P02. You can do the by taking some example. Understanding my point or not? You can take pressure value first, initial value. Then after that, you can take some other pressure value, and temperature value you can take some other value, and after that you can just calculate P02. Two values you can calculate, P02 and P02 dash. So before shock and after shock, you can just calculate. You'll be getting lesser value of stagnation pressure at that particular point. Understanding my point or not? If you are not able to understand by this particular meaning, so that I'm explaining in that way, right? Because everybody can understand why the temperature will increase, because H plus U square by 2, that is constant. So whatever the decrement in the velocity, that will be increment in the what? Enthalpy. And enthalpy is a function of what? Temperature for the ideal gas. As far as the ideal gas concerned, enthalpy is a function of temperature. Now, so these are the properties that we are getting when the normal shock occurring. Pressure will increase, P0 will decrease, V will increase, Mach number will decrease because velocity will increase, velocity will decrease, T will increase, T0 will remain constant, density will increase, and entropy will increase. Highly irreversible. Irreversible means what? dq by T plus entropy generation is equal to what? Delta S of the system. So this is 0 because of adiabatic condition. Entropy generation more than 0 because irreversible, and because of that, entropy of the system will be more than 0. That's the reason they mentioned that the entropy is increases. Understanding my point? All of you? Perfect. Note down oblique shock. Not all the shocks are occurring at the perpendicular to the flow direction. Some of the shocks are there that is happening at the inclined direction. Suppose this is a flow direction, but the shock may be producing at the incline to this one. at the some inclination to the flow direction, beta inclination. Suppose in that case, this shock will be called oblique shock. Whenever the oblique shock will happen, the flow has to be there supersonic before, but after that, the flow can be, after the oblique shock, the flow can be subsonic or it can be supersonic. Understanding my point? Unlike what we seen in the normal shock, the flow has to be converted from supersonic to subsonic, but here the flow can be subsonic and what? It can be supersonic flow also. So please note down, very, very important. What is the example? When the space shuttle travels at a very, very high speed, supersonic speed through the atmosphere, it produces a very complicated shock pattern like this. Suppose space shuttle is there, it is flowing in a particular medium, atmosphere medium, and the flow is happening, surrounding air is flowing like this. Because of that, the shock wave will be producing like this. This is the angle alpha, this is the angle what? Beta. Right? So this is what the oblique shock. That is happening at an angle with the flow direction, with some angle flow direction. But normal shock, what is the beta value? 20 degree. Most of the time, whatever the shock will be observed in the jet aircraft or rocket, you observe only oblique shock only. Shock means pressure will increase. That's the reason shock is also called compression wave. Right? Understanding my point? Is it done, all of you? So note an important point, very, very important point, I would say. Like normal shock, the Mach number decreases across the oblique shock, and oblique shocks are possible only if upstream flow is supersonic. However, unlike the normal shock, see, what is the meaning of statement number 1? Statement number 1 is saying that shock will always be produced when the upstream flow is what? Supersonic. Understanding my point or not? The flow, the shock can only happen when the flow is what? Supersonic. When the flow is subsonic, can never occur what? Shock wave. For both oblique shock and normal shock, the flow has to be what? Supersonic at the extreme end. First time, whatever the flow has to be there at this section, it has to be supersonic. But unlike the normal shock, in which downstream at the point 2, you can take to be upstream to be point number 1. The Mach number is always subsonic, right? Mach number always subsonic downstream of the oblique shock, but the Mach number in the case of oblique shock can be subsonic, can be sonic, can be supersonic, depends on the upstream Mach number, how strong the Mach number is, and the turning angle. Note down, guys, very, very important. With what angle it is turning that particular wave. So it depends on the two things, right? If Mach number is very, very high, suppose Mach number is equal to what? 11. Then after occurring the oblique shock, still if you if still we have the oblique shock, still the Mach number will be what? 1 or 1.2. So still it is higher than 1, we call supersonic. But if Mach number is initially very, very low, 1.2, that is not very, very strong. The moment the shock will be produced, velocity will decrease drastically and the Mach number will be less than 1. And that case we call subsonic, or maybe equal to 1. That is sonic. So that depends on the how much Mach number is there at the upstream ends. Understanding my point? And of course the turning angle, right? Of course the turning angle. Of course the turning angle, right? How much of angle you have tilted this particular diffuser section? Understanding my point or not? What is the diffuser angle? How much of angle you have tilted? If that angle is very, very sharp like this, large amount of shock wave will be producing, and that is oblique shock. Understanding my point or not? When the flow will be happening. All of you understanding what I'm saying? So again, that whole phenomena, whole derivation of each and every sock will be discussed in detail for the GATE course, but for HL examination, more than sufficient we have covered, right? In fact, if you just write for the GATE examination also, you can check it out. You can easily answer all the answers, whatever the question they have asked in past 2 years, that is in 2021 and in 2022. All the answers you can answer comfortably, whatever the question is there, right? Yes or no, guys? Yes. Now, once it is done, let me know. We can discuss some of the example. Is it done? Yes. Are you there? Hello, hello. Hello, hello. I'm audible. So before also I was audible, right? Because my basically mic was different. Before I was audible comfortably. Okay, fine. Okay. So now tell me the answer for this question. A shock wave is produced when the flow changes from supersonic to subsonic. C will be correct, right? Perfect. Why the shock wave cannot produce in the converging section? You got the reason, right? In the converging section, my dear friend, the flow is what? Subsonic only. The flow is subsonic only. See, in between 1 and 2 section, still the flow is what? Subsonic. Because of that, the temperature will be low, pressure will be low, entropy might be possible that will be getting less than 0. If entropy will be less than 0, entropy generation is what? Less than 0. Is it possible to have entropy generation to be 0, less than 0? Not possible, right? Temperature value will be such a low that it cannot happen. The shock cannot be produced. Shock can always be produced when the flow is happening in the possible flow directions. When entropy will increase, that means there is an increment in the entropy, and from the second law of thermodynamics, the flow always occur in the increase in the entropy. The flow will always occur at a point where the entropy has been increasing. In the increment direction of the entropy, the flow is happening. Understanding my point or not? Perfect. So it has to be possible that supersonic to subsonic, subsonic to supersonic, subsonic to supersonic will never be possible. That's the reason in the converging part, we'll never come across any shock wave. All the shock phenomena happening in the what? Divergent portion, right? Across the normal shock, what will happen? The pressure and temperature both will shoots up, right? If they mention only temperature, that means assume static temperature, not stagnation temperature. Yes or no, guys? Done? Perfect. So that is all about the course, my dear friend, that we have covered. So in the next segment, we are going to cover in the fluid machinery, right? Whatever the Pelton wheel is there. And then we have, Francis turbine, Kaplan turbine. What is the for high discharge, for low discharge, for high head value or low head value? Those things we are going to cover. And of course, we are going to cover centrifugal pump also, along with some part of the axial flow pump, right? or maybe you can call centrifugal pump. Yes or no? Okay, guys, thank you. Yes.